A fluoropolymer arises from a fluorocarbon-based polymer structure containing many carbon-fluorine bonds. These polymers stand out for their substantial resistance to solvents, acids, and bases. The most widely recognized example, polytetrafluoroethylene, is commonly referred to by its brand name Teflon, once associated with its original creator. The accidental discovery of polytetrafluoroethylene in 1938 occurred when Roy J. Plunkett was experimenting with tetrafluoroethylene gas for refrigerant development. Upon finding a previously pressurized container void of pressure but filled with a solid, the material was investigated and identified as a type of polymer previously unknown. Fluoropolymers exhibit traits typical of fluorocarbons, such as reduced attraction between molecules compared to traditional hydrocarbons, which imparts widely known non-stick qualities and decreases friction. Their remarkable stability is due to the presence of multiple carbon-fluorine bonds. From a material science perspective, fluoropolymers can be categorized either as thermosets, which do not melt upon heating, or thermoplastics, which can be reshaped. Structurally, they can be formed from a single type of monomer, known as homopolymers, or from a combination of different monomers, known as copolymers. Perfluorocycloalkene, ethylene, vinyl fluoride, vinylidene fluoride, tetrafluoroethylene, chlorotrifluoroethylene, propylene, hexafluoropropylene, perfluoropropyl vinyl ether, and perfluoromethyl vinyl ether are fundamental monomers forming the backbone of various fluoropolymer compounds. These monomers combine in diverse configurations, yielding materials with distinct characteristics, such as high melting points and chemical resilience, suitable for a multitude of applications. Polyvinyl fluoride, marketed as Tedlar, is derived from vinyl fluoride and possesses a melting point near 200 degrees Celsius, providing protective qualities in films and wraps. Polyvinylidene fluoride, found in products like Kinar and Solef, results from vinylidene fluoride monomers and melts at about 175 degrees Celsius. Polytetrafluoroethylene, recognized commercially under names such as Teflon and Algaflon, is created solely from tetrafluoroethylene and exhibits a high melting threshold at 327 degrees Celsius, which leads to its widespread use in applications requiring non-stick or chemical-resistant surfaces. Polychlorotrifluoroethylene, available as Neoflon and Kel-F, originates from chlorotrifluoroethylene monomers and melts at 220 degrees Celsius. Perfluoroalkoxypolymers, such as those sold as Hyflon or Teflon PFA, are synthesized from a combination of perfluoropropyl vinyl ether and tetrafluoroethylene and melt around 305 degrees Celsius. Fluorinated ethylene propylene copolymers, including those identified by the names Teflon, FEP, and Neoflon, use hexafluoropropylene and tetrafluoroethylene and melt at 260 degrees Celsius. Polyethylene tetrafluoroethylene, encountered as Fluon ETFE and Tefzel, is formed from tetrafluoroethylene and ethylene, melting at 265 degrees Celsius. Polyethylene chlorotrifluoroethylene, such as Halar, results from the blending of chlorotrifluoroethylene and ethylene. Elastomers within this family, including perfluorinated elastomers and fluoroelastomers, are constructed from varied degrees of fluorinated monomers, yielding commercial versions like Calrez and Viton that exhibit flexibility alongside strong resistance to solvents and high temperatures. Other products such as AFLAS, tetrafluoroethylene propylene elastomer, and perfluoropolyether fluids like Krytox further illustrate the versatility of combining these key monomers. Perfluorosulfonic acid polymers, with an example like Nafion, demonstrate remarkable stability in aggressive environments. Each material's performance depends on the ratio and structure of the base monomers, granting unique physical properties that shape their use across aerospace, electronics, and chemical processing scenarios.